Okay, this presentation will relate to the gamma distribution. So, in this question what we're told is that there's a certain metropolitan city where the daily consumption of electric power in terms of million kilowatt hours, MKH, may be regarded as a random variable having a gamma distribution with parameters 3 and 2. Now, just to sort of start off with, there are actually other variant ways of specifying the gamma distribution, but I'm using one where I will use the shape and scale parameter, okay, as a default one. If that's my default setting for the gamma distribution. In other questions, I will, if I am using a different specification, I will make it a bit more evident. But this is the shape and scale parameter, okay, 3 and 2. Now, the variable of interest here is the daily consumption of power. So that's our x variable there, okay. So let's continue. If the power plant has a daily capacity of 12 MKH, what is the probability that this power supply will be inadequate on a given day? That means what is the probability that x is going to be greater than 12? So 12 is like a maximum. So let's just say it supplies 12 every day. What is the probability that demand will exceed 12? That would be inadequate, an inadequate supply. So essentially this is what we're asked here. Probability of x greater than or equal to 12. Okay? Well, greater than 12 really. But it doesn't really matter so much when it's a continuous random variable. So this is the gamma distribution, and this is the way we're specifying it. And again, just in case there are other ways of specifying the gamma distribution, but if I am using a question with a different specification, I'll make it clear. So this is the shape and scale parameters, k and theta. So k here is equal to 3 and theta here is equal to 2. So this is the main specification of the probability density function here. Okay, so I was just checking a few things there before I started. But just to make it a little bit easier to read, I just re-expressed that as follows, okay? So f of x, where x is greater than 0, equals 1 over gamma of k times theta to the power of k times x to the power of k minus 1 times the exponential of minus x over theta. Okay, so there's quite a lot going on there. Now, but remember, k is equal to 3 and theta is equal to 2. Okay, so we can sort of start to simplify this expression here. Theta to the power of k is simply 2 to the power of 3, which is 8. Okay, the gamma function, gamma of theta is the gamma function, and for all positive integers, gamma of theta equals gamma of alpha, pardon me, equals alpha minus 1 factorial. So alpha minus 1, calculate that and then get the factorial of that. So gamma of 3 equals 3 minus 1 factorial, which is 2 factorial, which is equal to 2. Okay, so when we piece this all together, this is 1 over 2 times 8. Okay, x to the power of k minus 1 is x to the power of 3 minus 1, which is 2, and theta is equal to 2. So we have the exponential there of minus x over 2. Okay, so that's just a bit of old junk there. You can disregard that. So essentially what we have there, so we sort of pieced it all together. Okay, and so this is for our specification with 3 and 2, we can simplify the PDF as follows, or just put in some numbers there. And again, just using make it a little bit clearer that this is essentially the key function that we are looking at there. F of x, small f, equals 1 over 16 times x squared times exponential of minus x over 2. Okay? So essentially this is an integration question. Okay? So a lot of what we're going to do from now on is essentially integration. And you'll just actually look at it. This is I'm going to sort of focus in on this part here. Okay? X squared times the exponential of minus x over 2. And if you're feeling that this is a an integration by parts question or a calculation, you're not wrong, okay? So essentially this is what we're doing here. So this is really integration by parts. Now, really, if you're doing gamma distributions and stuff like this, you probably want to have seen differentiation and integration before, and be familiar and comfortable with integration by parts, because really this is a fairly textbook example of an integration by parts question. Okay, but I'll just go over the basics of it quickly. U is equal to x squared, and that means that du is equal to 2x times dx. dv is equal to the exponential of minus x over 2 dx. Okay, so when we integrate that out, we get minus 2 times the exponential of minus x over 2. Okay, sorry, this is the fundamental formula for the integration by parts there. Okay, so really there should be nothing too troubling here. The one thing about it is, though, that you want to spend a lot of time with these questions there. So this is how we would sort of progress matters here. Okay, so just use our standard formula there, u times v minus the integral of v du. Okay, just piece it all together there. But what you'll sort of see here is when you get down here that you have to do another integration by parts here. So that's what I'm going to call I2. Okay, I2 here. Okay, and essentially just do integration by parts again. So it's a composite integration by parts there. Okay, I2 is the integral of x times the exponential of minus x over 2 dx. Okay, so same thing again. Okay, here rather than u and v, I'm going to use a and b. Okay, but it's really the same idea. It's just keep my notation as distinctive as possible. Okay, a is equal to x, dA is equal to dx. Okay, dB is equal to the exponential of minus x over 2 dx, so we get that back. Okay, b. Okay, and when we piece it all together there, the I2, which is the second integral, equals AB minus the integral of BdA, and just piece it all together there, and the exponential of minus x over 2 dx, which is minus 2 the exponential times the exponential of minus x over 2. So that's where that plus 2 becomes minus 2. Essentially, I won't go, this is integration so of an exponential, so you really should not be having too much trouble there. So if you are, this is the wrong question to be. Gamma distributions, gamma functions, and so on are the wrong place to be learning about integration by parts. But essentially what we should do is be able to piece it all together there. Okay, so ultimately the integral should end up as follows. Okay, so the exponential of minus x over 2 times minus 2x squared minus 8x minus 16. Okay, so the question really is probability of x greater than 12, greater or equal to 12, but 12. So now this is so that's what the question asks us, and essentially how would we express that as an integral? Well, that is an integral from 12 to infinity. Okay, so f of x times dx. So essentially what we have there, 1 over 16. So I set it up down here. So this is where we got to. So essentially our integral is, sorry, actually that's what I was reminding myself there. We have 1 over 16 that I took out of it earlier on. So the integral, evaluate this from 12 to infinity, and yeah, as I said, don't forget that 16. So when we evaluate it for infinity, essentially what we'll end up with is 0 times infinity. Okay, somebody just sort of commented on that's not exactly equal to 0, but for the purposes of probability, you know, it's not 100% correct to evaluate that as 0 mathematically, but for the purposes of probability, when we evaluate that expression at infinity, it's okay to say 0. Okay, for all intents and purposes. So essentially what we do now is evaluate it for 12. Okay, so it's at the lower limit of the limits of integration. Okay, evaluate it by 12. So the exponential of minus 12 over 2, which I have down here, and we have that quadratic expression minus x squared minus 8x minus 16. When I evaluate that for 12, that's 288 plus 96 plus 16. That all divides by 16. Okay, we have a minus here and a minus here. They'll cancel out. Okay, so the 0 minus minus, that cancels out. So we end up with 400 over 16 times the exponential of minus 6. That's 25 times e to the minus 6, exponential of minus 6. So that works out to be 0.062. Okay, so less than 1%. Okay, now, so there was a lot involved in this, and a lot to do really was about integration by parts. Okay, and sometimes you just can't avoid it. Okay, and you get fairly long questions. This actually doesn't look like a big long question, but it actually does turn out to be a big long question. Anyway, we leave it there.